Molar volume. The idea of molar volume comes from the idea that when pressure and temperature are constant, and maybe I blew up a balloon with a certain number of moles in it, it has some volume. Okay, so let's say there was 5 moles here. If I blow up another balloon in the same room, so same temperature and pressure, and I put the exact same number of moles in it, n equals 5, the volumes should be equal. So what we know is that at SATP conditions, 1 mole will have a definite volume of 24.8 liters. So the idea is that if I have less than 1 mole, I will have less than 24.8 liters, but it will be proportional. So according to Avogadro, when pressure and temperature are constant, volume and the number of moles of gas present are proportional to what we know. So the molar volume is equal to the volume of the balloon divided by the number of moles, where the molar volume at SATP is 24.8 liters of gas per 1 mole of gas. Now, because we have a condition at SATP, we also have one for STP. Now, STP is a little bit cooler. The pressure is slightly different, but the fact that it's cooler, we have a smaller molar volume. So 1 mole of gas at STP will occupy 22.4 liters. Again, these are the constants that would go into VM. And then the number of moles and the volume would be what would be changing in each scenario. So let's try it. What chemical amount or number of moles of propane is contained in a 20-pound tank, or 17.78 liters, if the gas is at SATP? So within the tank, we know that it's not actually 20 pounds anymore, because the tank's pressure is SATP, okay? Now, normally a tank is at a high pressure, so we know that it's basically empty, that it is equal inside and out. All right, so VM, well, we're looking at SATP, so the molar volume at SATP is 24.8 liters per mole. This is a constant. And this is on the back of your periodic table, at the bottom right-hand corner in measured or uncertain quantities. We also have the volume of the tank, 17.78 liters, which is slightly less than the molar volume, what the tank would be if 1 mole were present. Therefore, I know that there's less than a mole. But to figure out exactly what we have VM is equal to V over N. We're solving for N, which is currently in the denominator. So the first step is that we need to multiply N out of the denominator. So N cancels on both sides, and I'm left with N times VM is equal to the volume of the tank. Remember, VM is a constant, and it is different than V. All right, we're going to divide both sides by VM to get N by itself, and I'm going to use the formula N is equal to V over VM. So the number of moles then is 17.78 liters divided by 24.8 liters per mole. And this gives me a number of moles of 0.716935, and that's moles. The only measured value that we used was this 17.78, which was 4 significant figures. Now, I recognize that our molar volume only has 3 significant figures. I'm sure we could look up a more accurate molar volume if we'd like. So in this case, I would go with what is in the question, the measured quantity in the question for significant digits. So I would round this to 0.7169 moles of propane. However, knowing that this one had 3 significant figures and it was a value we used, I would also accept 0.717 moles of propane. Both would be acceptable for significant figures. Another example, an oxygen tank's mass decreases by 3.6 kilograms over the course of 1 day. What volume of oxygen at SATP was used that day? I'm going to do STP just because we just used SATP. And what we have is mass. It was 3.6 kilograms. I'm looking for volume. And I have a molar volume. And again, it's at STP. So that's 22.4 liters per mole, again, on the back of your periodic table. Remember that Vm is equal to V over N. In this case, we're being asked to solve for V. So we need to find N. Given that we have mass, we can use our formula that N is equal to little m over big M to find out the number of moles that 3.6 kilograms of oxygen represents. Let's write the formula for oxygen, and we're going to calculate its molar mass. Remember, oxygen is diatomic, so it's always coming in twos. Therefore, the molar mass of oxygen is 2 times the molar mass of one oxygen atom, which is 16.00 grams per mole. Therefore, we're going to get a molar mass of 32.00 grams per mole for oxygen. We're noting that the unit is grams here. We need to turn kilograms into grams. So 3.6 kilograms. I'm going to use unit conversion just to show. We need to change kilograms into grams. I know that there are 1,000 grams in 1 kilogram. So I'm going to put that piece of information in here. There are 1,000 grams per 1 kilogram. So in this case, I'm multiplying by 1,000. If you knew that off the top of your head, that's fine, and you can go ahead with that. All right, we are now ready to calculate the number of moles. So N is equal to M over M. I did just have that formula, but I'll write it out one more time. So 3,600 grams divided by 32 grams per mole. I get a number of moles, of 112.5. That's lots. So I am now ready to look at my VM formula because I have moles, I have molar volume, and we can now solve for V. So Vm is equal to V over N, multiplying both sides by N. I get that V is equal to N times Vm. So 112.5 moles of oxygen times my molar volume at STP, which was 22.4 liters per mole. And I get 2,520 liters. Now, in my question, I only had 2 significant figures. So my final answer needs 2 significant figures as well. Decimal point is technically here. I cannot represent a number with a thousands place with 2 numbers without using scientific notation. So we're going to move the decimal 3 times. I get 2.5 times 10 to the 3 liters. You could also report this as 2.5 kiloliters. The unit wasn't specified. It's really up to you. Either of these answers would be acceptable, but we do need only 2 significant digits in this case. There's some practice in the Nelson textbook for you to just make sure that you are ready for that assignment.